Thank you all for attending. This the 25th or so, I've lost count, annual Isaac Asimov panel debate. I'm Neil deGrasse Tyson, your personal astrophysicist. And I also, after that, I serve as the Frederick P. Rose director of the Hayden Planetarium. And this is our annual event. This was started in the year 2000 with interest from the family of Isaac Asimov, at the time, the late Isaac Asimov. Something I didn't know until I was told is that of his 600 books that he's written, most of them were researched at our research library here at the museum. And so the legacy, it's quite a legacy to leave, and we wanted to make sure we had a living memorial to him. And that is this event. Are we all aware of the topic this evening? I met some people outside, they said, oh, what are we doing tonight? And I said, that's love, because you're coming without even knowing what the subject is. It is the James Webb Space Telescope's cosmic revolution. There's observations made in the early universe that were very difficult to explain, given our prior understandings of how the universe should have worked back then. And we figured that was the right time and place to make that the subject of this year's panel. I will be introducing the panel. You'll get to hear their voices initially, you can warm up to them. Then we'll get into our conversation. This event, you should think of it as you are eavesdropping on a conversation we are having in like the breakout lounge of a scientific conference, okay? That's how you should think about what we're about to do. And I'm a little bit of an interlocutor, so if there's something that I think you might not understand, I'll break in. But mostly it's scientists being scientists among other scientists. And this is what we all look forward to. So, thank you. Let me bring out the panel, and we'll learn about all their expertise shortly thereafter. First, a very longtime friend and colleague. We came up through the system of astrophysics together. Wendy Freedman from the University of Chicago. Wendy, come on out. From the University of Texas at Austin, Michael Boylan-Kolchin. I think I pronounced the Kolchin. Yes, Michael. And next, right from the CCA, right downtown, we'll learn more about that institution in a minute, is Rachel Somerville. Rachel, come on out. Neighbor. And from Georgia Tech, Georgia in the house, John Wise. John, come on out. And fifth on our panel is from Yale University, right up there in New Haven, Connecticut, Priya Natarajan. Priya, come on out. Everyone here is an expert in some way regarding data, simulations on a computer, and observations of the early universe, especially with regard to galaxies. And we're going to find out why that matters in a minute. So Priya, tell us, what is your professional interest and specialty?
So my expertise and interest is really in the invisible universe, so the dark components that we have to infer about dark matter, dark energy, and black holes.
So when you say invisible, you don't mean just that a telescope doesn't, you don't mean that the human eye doesn't see it.
No, I mean more than that.
Yes.
There is no light in any wavelength that is emitted by these entities. And so you infer their presence indirectly. And it turns out that they play a very important, if not starring role in the universe.
Maybe more of a role than the stuff we can see.
Absolutely. And
That's kind of spooky, you know.
Yeah.
You're saying you're an expert on stuff we can't see,
Right.
that's more important than the things we can see.
Yep.
Okay, just want you to remember how weird that is.
Well, the hidden is always more important than what isn't right in front of your eyes.
That's poetic. The hidden is always more important than what's in front of your eyes. Thank you for that. So John, up from Georgia Tech.
That's right.
Peach country. Yes.
Yeah, Peach State.
Peach State. So what, your expertise lands where?
I do computer simulations on some of the largest supercomputers in the nation of the first stars and galaxies in the universe, trying to see how they actually form from scratch.
Okay, because you can't observe that, you have to simulate it.
That's right, yeah. Not even James Webb Space Telescope can see the smallest galaxies.
Okay, so we have to trust that you're putting the right input.
That's right, yes.
Okay, we'll get back to that.
Okay.
Rachel, you're from the CCA, right on
Correct.
downtown. Just that's a new institution. Just give us a minute on what that institution is and what brought you to them.
So the CCA stands for the Center for Computational Astrophysics, and we are one of 5 centers that are part of the Flatiron Institute. And the Flatiron Institute is supported by the Simons Foundation, which was started by Jim and Marilyn Simons. And each of those centers works on a different aspect of computational science.
So I think biology is one of them as well. Is that right?
Biology, neuroscience, math, quantum physics, and am I forgetting one? And astrophysics. There we go.
Okay, and so your specialty is?
So I like to say that I make galaxies on the computer. And I also make some supermassive black holes to make things interesting. And I was also part of one of the teams that planned some of the first observations that James Webb took.
Okay, so you helped to guide you had some of this, you had the steering wheel.
We had some say into where Webb pointed when it was first switched on.
Interesting, okay, we'll get back to that.
All right.
Definitely. Michael, up from Texas.
Sir.
How you doing? So where do you come, what's your cosmic interest here?
Well, I also work on dark matter. I'm a theorist. I use big computations simulations. I also do pencil and paper work as much as possible. And my interest is in the sort of descendants of the first galaxies that John is studying. So I look around us at maybe their fossil remnants.
Wait, he just said he made galaxies. He didn't say he made the first galaxies. Was that the same thing?
Well, John, I think, studies
Make the first galaxy.
Okay.
first galaxies.
All right.
Some of the earliest galaxies to form, so we can't see them directly when they're forming with JWST even, but we can see them around us today, the fossil remnants, and so we can study them very well around us in the Milky Way. So I study those galaxies to tell us about dark matter and what was happening at the earliest phases.
Okay. And Wendy, we go way back. Wendy? Wow.
Don't tell.
No, it's an important piece of history because we predate the Hubble telescope when it was launched, and you had a big say in what the Hubble telescope would do first, where we pointed it first, and why, because at the time, our understanding of the age of the universe was uncertain by a factor of 2. That should have been more embarrassing to us than we had felt at the time. But you were going to do something about that. So just give me a backstory there. What happened with Hubble and your role in it?
So backstory, that's right. We didn't know the age of the universe to better than a factor of 2. Was the universe 10 billion years old or 20 billion years old? And
But were you confident there was somewhere in between the 10 and the 20?
It would have been unlikely that it was outside, but not out of the realm of possibility, given our ignorance at the time. And so one of the primary reasons that the Hubble Space Telescope was built, in fact, was to resolve this problem, solve the debate. And
So the motivation
for building Hubble. And in fact, the size of the primary mirror was set to be able to observe the stars that we use to measure distances, called Cepheids, with the Hubble Space Telescope at the Virgo cluster.
Wait, I thought the size of the mirror was set by the payload bay of the shuttle.
That was another factor. But
if we made it an inch bigger, it wouldn't fit in the shuttle.
True, but if you could have made it smaller and it would have been cheaper, and the reason it wasn't made smaller was to be able to resolve this debate.
Got it.
So the director at the time of the Space Telescope Science Institute put together a panel of people that said, what are the most important projects Hubble can do? Resolving this problem was number 1, and he made what he called key projects, big telescopes, he said, big projects. If Hubble were to fall in the ocean and it hadn't done something, we'd never know what the answer was. So what were those projects? And measuring this Hubble constant, the expansion rate of the universe, was the highest priority.
I hadn't thought about it that way. So the key projects were, if something unforeseen bad happens to the telescope on orbit, the first things we would have had the first and most important projects resolved.
Yeah, and he was afraid that if he put together a committee to decide who got the time, the committee would slice it into small pieces to give more people time. And so some problems required more time, and so he designated those as key projects with a lot of time.
And you got a key project.
Got a key
You got a key project. So you are on the main paper that settled that argument. And so where did the age of the universe show up on that paper back then?
13.7 billion years.
Sounds like you nailed it.
We nailed it. It's held for the 20 years since 23 years now since we published our final paper. That's the value. Using that method that we used with Hubble has not changed.
All right, Michael, do you agree with that age of the universe?
Well, I think that there's an alternate way you can measure that age, and that's with the cosmic microwave background, the light from the earliest phases of the universe, and studying its properties statistically tells you about the components.
Wait, so how did you get the age of the universe? If you didn't use the microwave background, what did you do?
So we're measuring galaxies nearby, and we're measuring how far away they are and what velocities they're moving at.
At the expansion of the universe.
And that's the expansion of the universe, which you can extrapolate backwards, essentially, using a cosmological model and determine the age of the universe.
In fact, that's what Edwin Hubble first did back in the 1920s. Did that have something to do with why they named that telescope after him?
It did indeed. It wasn't an accident.
It wasn't an accident. Okay. Okay. All right. So now you're going to not look at galaxies. You got a back door to the age of the universe.
That's right. We're looking at actually the other edge of the universe, as far away as we can see, the very first light in the universe. And that tells us properties of the universe at the very earliest times. And that, combined with a cosmological model, also gives us an age. And that age is 13.8 billion years with an uncertainty of only 25 million years on it.
So you want us to care that her answer is 13.7, your answer is 13.8, but that difference matters to the two of you.
Well, I think that difference...
But I grew up, I came up with a factor of 2 difference.
Well, what's 100 million years between friends? I get you, but I think there's a bigger issue that the way we measure the Hubble constant locally, that Wendy has really worked on and been an expert in and pioneered, there are different numbers that the different groups get sometimes, and there can be a number that would give a different age, a younger age of the universe, more like 12.8 billion years. And so a billion is starting to get to be an issue, perhaps.
So there's tension in the early universe.
There may be.
Agreed.
Rachel, do you have any reflections on the age of the universe, or you're cool with whatever they tell you?
I'm pretty much cool with that. Galaxies don't care that much.
Yeah,
As long as the stars are younger than the universe, I'm good.
Oh.
Yeah, we have a problem if that's not the case.
Yeah, that was a problem back when I was in graduate school.
Yeah, so you're telling me I think I remember this. There was a time when someone discovered stars that were older than the age of the universe you all were telling us. And this was like big headlines. That's embarrassing. Yeah. So how was that resolved?
That was resolved by discovering that the universe is accelerating and getting better measurements with Hubble, those 2 things.
Oh, well, this is not about the accelerating. Well, it might be. We might learn more about this from Priya in a minute. So this age, so where should we take the age right now? Just tell me, who do we believe? Well, no, let me not cause a fight. Let me just say, these are 2 methods that in and of themselves are sound, yet they give 2 different answers that do not overlap in their uncertainties. Mm-hmm. So something has to give.
Right.
Who's going to yield here?
Well, I think the interesting part of this, so there are at least a couple possibilities, right? There might be something wrong with the data that is misleading us, or it could be that there's something missing in our model, our standard model that has the dark energy and dark matter we've been talking about, and that there's another physical something that we have not yet discovered, and this might point to that. And so the question is, can we find something in the data that might be misleading us, or this more exciting possibility, I think all of us would be very excited at the idea that we could learn something fundamental about the early universe by comparing these values. Because there's only, we live in one universe right now, and these numbers are not matching. They should match. We're coming from high redshift, coming from low redshift, and it's like we're digging a tunnel on opposite sides of a mountain, and we missed. So is it important or not? And that's what we're trying to...
So Michael, you sounded more confident about your answer than Wendy sounded about her answer.
Well, as a good theorist, I could argue any of the answers, hopefully, and whichever answer.
That's a good theorist,
Yes,
arguing any answer.
That's right.
Not a bad theorist.
Well, I think that one angle that I'm very interested in, and I think is becoming interesting again, is this question of the oldest objects in the universe. Since there is this discrepancy, we can go back and ask now with better instruments, JWST, other observatories, can we do better in age dating stars and star clusters? Because if we can say the oldest star clusters are definitively older than that younger age of the universe, then we're back to saying that is probably the wrong answer.
Got it. So Rachel, in the early universe, what is it that the James Webb Telescope found that sent everyone into a tizzy?
So I think there are two things that have sent us into a tizzy. One is that Webb found a lot of very luminous galaxies at very, very early times, pumping out huge amounts of ultraviolet light. And the theories that had been published before Webb launched did not predict that large a number of such bright galaxies. So that caused a big fuss. And then a little bit later, we started to find evidence for supermassive black holes that were also much larger, much more massive, and at much earlier times than theory had predicted. So, and maybe those two things go together, right? But so the problem is sort of too many, too bright, too massive. How did we make these things so?
So we underpredicted the energetics of the early universe. Is that a fair characterization?
I like that way of characterizing it, actually. So one of the first analysis, which was done by our friend here, was based on how massive we thought these objects were. And the masses are actually quite uncertain.
Masses of the black holes or of the galaxies?
So now I'm talking about the galaxies. Mm-hmm. So the mass of stars in the galaxy is not something we can observe directly, right? We observe the light, and specifically we observe the ultraviolet light primarily for these early objects because the light is redshifted as it travels to us.
Well, just to clarify that, the James Webb Space Telescope is exquisitely tuned to see infrared light. And you're speaking glibly about the emission of ultraviolet light in the early universe. Neil.
Yes.
So what's going on here?
So what's going on is that, as we have discussed, the universe is expanding, and as light travels to us for the 13.6 billion years and change.
13.6?
From... No. Remember, it took some time.
It's just the galaxy. That's the whole
universe.
The galaxy. It's just a galaxy. Thank you.
So it took a couple 100 million years for the galaxy to form.
Couple 100 million years.
Right. And then that light, as it travels to us, the wavelength is what we call redshifted. That's why it's called a redshift, right? So the wavelength gets longer, so it's emitted in the ultraviolet, but by the time it gets to the Webb, it's in the infrared.
So we knew this in advance.
We knew this in advance. This is fundamental physics.
So the James Webb Space Telescope...
It's almost like they planned it, right?
...was conceived to be exquisitely sensitive to the formation of galaxies, knowing that they emit copious ultraviolet light.
And in fact, this is one reason that Hubble was not able to push beyond a certain redshift. So there was sort of a redshift limit, if you like, a hard limit that Hubble could not push beyond, partly because it's smaller, its mirror is smaller, so it can't collect light as well, so it couldn't see the faint objects, but also because it couldn't see far enough into the infrared, which now Webb is allowing us to do.
John, tell me about black holes in galaxies. Why are they important at all?
Yeah, so today we see black holes, supermassive black holes at the center of all galaxies, but
All galaxies we've looked at.
yeah, most massive galaxies we've looked at. But in the early universe, that's not always the case. And it's a big question of which galaxies form supermassive black holes and which ones don't. And where did these supermassive black holes actually come from? And we call these like the seeds of the supermassive black holes. So, it's a big question whether they start big or small. Because when you look with JWST, back then the supermassive black holes might be nearly as big as the stars that in the galaxy that contains it. But nowadays it's 1 part in 1,000. So they're so much more massive. Today, but fractionally compared to the galaxies back then, they're much larger in relationship to their stars.
I get it.
Yep.
So Priya, I think what he's saying here is that we're still forming things.
Yeah.
So you can get a black hole not as massive then as today, but a much bigger fraction of the mass that would be collected to become a galaxy.
That's right.
So is it fair to say that black holes are seeding the galaxies?
I think that's the big open question as to which comes first. I think the question, though, is that we know that they grow in tandem, but occasionally you could start out with a small black hole seed and stars forming around it in the host. We believe that all black holes actually need a host galaxy. They're not sort of naked black holes floating around.
Oh, okay. So the galaxy comes first.
I think it remains to be seen.
You just said!
Well, there is a class of black holes that you could make potentially in the very early universe, the infant universe, called primordial black holes. And those would supersede the formation of anything material that we know. But we don't know if they exist.
But we don't
yet.
think that those are the seeds of the black hole.
No, but I mean, they could exist though, right?
they could
They may not be the seeds of the black holes that we are seeing in the centers of all galaxies nearby, but they could have been seeds of some very early galaxies, for example. That remains to be seen. The problem is that once you see a black hole, you have no idea where it came from. Mm-hmm. Because there is no information about where the mass that fed this black hole came from and how it formed. So the only way we understand where a black hole could have come from, and as Rachel said, they're much more ubiquitous, so there have to be multiple ways to form them, is the relationship between the mass of the black hole seed and its host galaxy, its parent galaxy.
Because the galaxy is going to feed it, ultimately.
The gas from the galaxy is going to feed it, but stars form from the same gas.
Okay.
So as John mentioned, in the very early universe, if there is a special way to form black holes, and a bunch of us predicted several years ago that there has to be more than one way to make these black holes, you could make some black holes that were really massive from the get-go, massive seeds. And we happen to find evidence for that from JWST.
All right, but John, how do you just create a supermassive black hole? Is that just a knob you turn in your software?
No.
And then say, oh, it matches, so I must be right.
No.
Wait. How many knobs are in your software?
I have many, many knobs, but it takes an expert.
I'm just saying, if one of them is the temperature, the age, the size, the mass distribution, and everything is an adjustable parameter, and you adjust it until it matches, what confidence should any of us have that your configuration of knobs is the actual universe?
No, that's a great
and you're just not over-supplied with ways to match what you have to match.
Yeah, because
you're not publishing papers where you say, my models don't match this. Here's my No, it's going to match it. Because that's why you're publishing the paper.
That's right.
But why should I have confidence at all?
Yeah,
And you do some of this too.
I know.
Don't you do? That's a question for both of you.
Yes.
Okay. What?
No, I have to build my own confidence.
Here. Okay, go.
I have to build my own confidence in the simulation because, the universe is a very complex place, and so are our simulations. So we do these test simulations in which we can actually compare our results from our simulations, say a single supernova, right? We have one injection of an energy, you have a star dying, and you see how it expands. And we do many of these tests in which we can actually compare it to analytical solutions. Because once you put together all these processes together in a supercomputer simulation, you can't predict how they're going to interact, but you gain confidence from these test analytical simulations.
So you've done it in pieces initially before you can gain confidence in the entire system.
Yes.
Okay. And are your computers as powerful as his? He said he used supercomputers.
I use supercomputers occasionally too, but I also work on the storyline of the universe. So there are patches that you simulate one patch at a time. Then I use his simulations to tie them all together, and then I confront the data from every epoch in the universe, what the simulation is telling us.
Okay, so she uses real data.
I compare against Priya.
You do?
He does too.
He does too. Oh, okay, all right. Rachel, remind me, what are the dark ages in the early universe? What is that?
So as Mike mentioned, the first light in the universe was actually sort of the glow of gas that was left over after the Big Bang. And after that...
Which we observed.
Which we observed as the cosmic microwave background radiation, exactly. And after that, there were no stars, there were no accreting black holes, there was nothing producing any light. So we call that the Dark Ages, and the Dark Ages ended when the first star in the universe, presumably it was a star, was born and started to emit light.
About how much time was that delay?
We think that was between 100 and 200 million years. We have not yet seen those first stars, we don't think. Even JWST is not powerful enough to see them. But our theory predicts it should be around 100 to 200 million years after the Big Bang.
All right. John, last I read, JWST found galaxies in the Dark Ages.
Well, I don't think there's any galaxies in the Dark Ages that they found, but they found very...
Oh, wait, so you're saying you're right and the James Webb Space Telescope is wrong.
The James Webb Space Telescope doesn't have feelings, so I think it'll be okay. But,
it'll survive this assault on its integrity.
Yes. What I think they have found are certainly galaxies earlier than we've ever seen them before, but not what we really think of as really fundamentally the Dark Ages, when before the first stars in the entire universe formed. We haven't seen anything that far back.
So Wendy, if we don't look at the cosmic microwave background, but we have galaxies back then, doesn't that help figure out the age of the universe if you're in a galaxy mode by doing so?
So you're talking about observations in the early universe?
Yeah.
Shed light.
Yeah, and we've got some. Well, he denies them. He's in denial. That's fine. Just the ones declared, the James Webb galaxies that seem to hail from the Dark Ages. That gets you data even farther back than you ever would have used before. Does that help you tighten the age?
Well, I think as Michael was saying before, it's another way of getting at the age. It's a way of doing this in a very different way than we do locally. But I think one of the things surfacing in this conversation is that you need to understand a lot of things, particularly about stars, which we haven't gotten into, right? So what you see in the distant universe is the integrated light from a galaxy. You don't have the opportunity to look at individual stars.
You're just too far away to resolve that.
Too far away. These are smudges. They're not individual stars that you can see. And so stars might have a very different history of, in the galaxy, different history of star formation, different metal abundance, different amounts of reddening, different kinds of dust that are causing the reddening, a different distribution of stars as they form.
When you said metal abundance, we're in the early universe. How much heavy metal has been made yet, if it's all made in supernova? Wouldn't it be like zero heavy elements then?
Well, we're seeing heavy elements in the spectra of these objects.
Okay, let me ask it differently. Why are you seeing heavy elements early in the universe before we've had a chance to bust out some supernova and spread the heavy elements that it made into that environment?
Yeah, and I think that's the interesting question, right? And I mean, one of the exciting things about JWST is we had theories of how galaxies formed, but it's really nice to actually look and say what is happening. But then you're looking and you have to interpret what you're seeing. And there are a lot of more knobs, as you say, that can go into the models that will give you the same answer if you adjust them in the way that you can explain the observations. So there's additional challenge in interpreting the ages, is what I would say.
Right, a very big point, which I forgot to mention, John. You adjust your knobs and you get a result. So do you have a way to test what other adjustments of those knobs give you the same result?
So we compare against observations. So before James Webb went up, right, we had to compare against other simulations, and it was like, it was a big uncertainty. Are our galaxies actually realistic or not? And I guess looking back at it, I was always worried because our galaxies were more massive than other groups. And because we don't have the luxury of actually comparing it to observations in the present day, because a lot of other groups, they'd run simulations until the present day, but we really specialize in the first billion years after the Big Bang. And like once these observations of JWST came out, like they're much more massive or much brighter than expected. And that kind of matched with our predictions and kind of, made me feel good about myself and all that anxiety. Waiting on.
We feel good about you too. That's fine, John. Yeah, Priya, I loved what you said, where you stapled together the various slices of time,
Yep.
and then compare that with the data that comes to you from those slices of time. I'm still trying to understand, how does your understanding and research on black holes, how is that touched by anything JWST is finding? Because it's just finding this puddled light of early galaxies. Why do black holes matter back then? Does it tell you that galaxies formed sooner or faster? What is the clue that you're getting?
Well, it turns out that, till quite recently, till about 5-10 years ago, we believed that black holes sort of played a marginal role in galaxy formation because their masses were tiny compared to the stars.
Yeah, they're big. If you fell in, that'd be a bad day for you.
That's right.
So I just read recently, a month ago, we discovered the highest mass black hole ever in a galaxy.
That's right.
That checked in at, who remembers what that number, what was the number?
It was like 10 billion.
10 billion?
Solar masses.
Don't you love how astronomers, 10 billion, we're just so casual with astronomically large numbers. So 10 billion, and how big is the black hole in our galaxy?
It's just 4 million times the mass of the sun.
Oh, that's low.
Yeah. It's still supermassive because anything that's above 1 million is classified as supermassive.
It's still supermassive, but it's pretty lame compared to this other one.
It's pretty garden variety, yeah.
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 The black hole envy in the universe.
Right.
Yeah. So
in the
all right, so you got to deal with that.
right.
That this is going to make a difference in everything you say and think about the formation of galaxies.
That's right. So very early on in the universe, because there's only one big gas reservoir from which both stars get made, from cooling gas, and the black hole gets fed, there's sort of a competition for who gets the gas, right? So who grows more rapidly, whether it's the black hole or it is the stars. So when we see data from the James Webb, we're seeing the integrated light
Of both.
of both, but then we also have a spectrum. And so there are very specific spectral signatures. So as a function of wavelength, that's the amount of energy that's coming out, and we know what the features are for a growing black hole. And so we are seeing these composites. So you know you have a black hole in place that's actively growing, and you have starlight. So, however, the key thing to discover a rapidly going black hole is X-ray radiation from the black hole, because the gas gets heated in the vicinity. The dying gasps of the gas before it falls into the black hole, it starts to speed up and starts to get heated up, and it starts glowing, and you see X-ray radiation.
It is glowing so hot,
Yep.
it's giving off X-rays.
Yep. And so you should be able...
It's like million, how hot is it?
10 million?
10 million degrees.
10 million, 50 million. And so you should be able to see if the object was bright enough. So that's the big question here. Can you really reach the first black holes? You should be able to see it with the Chandra X-ray telescope as well as James Webb Space Telescope.
So James Webb, so the X-rays back then are what today?
They will still be X-rays because these are hard X-rays.
All right, so these are so X-ray-y.
Yeah.
Can I use that
That's
word?
right, yeah,
X-ray.
sure.
They're so X-ray-y that you can,
You
the
see
redshift
through.
represented
Yeah.
from that still puts them in the X-ray
Yep.
part of the spectrum.
Yep.
That just means we don't have enough words to divide up the X-ray part of the spectrum, it sounds like.
Well, there's hard and soft. So they've kind of, hard X-rays.
Which has nothing to do with what they feel like. They just have something to do with how quickly they will kill you.
Right. How energetic they are, right? How
Okay, so
energetic.
I did not know that. So those are still within their zone.
Yeah.
And look at the bias that we experience because we see visible light and we have like many words to describe all the colors in this very tiny range of the electromagnetic spectrum. And out here is just X-rays.
Well, because I mean, we live in an anthropomorphic, it's all attuned to our retina, right?
Yeah.
We can tell the difference.
I guess I'm okay with that, but I just think about, I like words to be precise.
So I think one of this is, finding a black hole, a galaxy that's harboring a black hole, seeing it both with JWST and Chandra is a surefire indication that you have an actively growing black hole. Because the complication is, if you don't see it in the X-rays, then you have to decode how much of the light is coming from the stars and how much is coming from the black hole.
Got it. Okay, so
There's uncertainty there.
So let me restate what I think you just said. If you had X-rays, it's smoking gun for a black hole. But X-rays are not a prerequisite for a black hole.
Yep.
You can have a black hole where the gas is not so hot that it's going to be giving you X-rays. So then you have to somehow tease that information out of the other, like the spectrum or the
lines, the features that you
in
see
the
in the
spectrum.
spectrum, and the shape of the spectrum.
Okay.
And that's sort of an inherent uncertainty. And the Chandra Space Telescope, given its resolution, it's a fantastic telescope. Given its resolution, it can't quite reach the farthest edge of the universe where JWST is reaching right now. So you need some clever tricks to be able to. You have to look at some very special places in the universe. Nature's telescopes.
You're telling the public that you perform tricks.
Absolutely.
In the research. Okay.
And magic.
Okay, but I'm still trying to get to the bottom of something here. Rachel, I'm still trying to understand. If we have galaxies in the dark ages, let's get back to, they're not supposed to be there. So what has to give? Are the data, is there something wrong with the data? Because that's happened before. You know this. We've had, who can remind us of this experiment, this measurement of the cosmic microwave background that was misinterpreted by the authors. And then everybody saw, wow, there's a new weird feature in the cosmic microwave background. Let me come up with a theory to explain it. And they came up with a theory to explain it, and they were all, yeah, I'm a theorist, I got this. And it turns out the interpretation of the original paper was flawed, exposing ambulance-chasing theorists.
So this was the BICEP result.
BICEP,
from about,
that's an acronym, what was it?
So I actually do not remember what the acronym is.
Okay.
But
It had
it,
to do with B modes, I assume. With
Wait, say that again? Say
It
again?
had to do with B mode, so going after gravitational waves in the early universe.
Okay, B mode.
Signature in the microwave background. So what you have to really be careful of is that there is also dust that causes polarization of the microwave background.
Just in our own backyard, in our own galaxy.
Can be in our own Milky Way galaxy, that's right.
And-
And so correcting for that is vital. in
They didn't do that correctly.
Somebody actually read off a slide at a meeting. This is the lesson. Don't do that.
Okay. So that makes me wonder, do your models correctly predict galaxies in the dark ages?
well, I think.
That's a yes or a no question.
Well, now or wait earlier? No, so my models wouldn't have predicted galaxies, and I don't think anybody's models really predicted how much activity there was then. And so that's really what
That's a
people.
surprise.
So I think that's a surprise to everybody. So that's what Rachel was talking about, that everything's happening faster. It's also what Wendy was talking about with the metals appearing earlier. Everything is happening faster than we thought in the early universe, and we
And
need
metals
to figure
are
out
what our people call anything heavier than helium on the periodic table of elements.
That's right. We have a very simple chemistry here: hydrogen, helium, metals.
Yeah, so this kind of freaks out chemists when they hear us speak to each other.
Yes.
And we haven't corrected that over the decades.
Not at all.
Okay.
X, Y, and Z.
Yeah, okay, so the metals, I interrupted you, I'm sorry.
Oh, no, I was just saying that it all paints a consistent and consistently new picture, that things are happening faster than the models had previously said. And we need to understand Is that something that was missing in our models of how the galaxies are forming at early times? Or is it missing something in our picture of how the universe was evolving at early times?
So, Rachel, what has to be adjusted?
Yeah, so I wanted to come back to the question you were asking before about how do we know our models are correct, right? And because, as John said...
Right, because just because they match doesn't mean
Yeah.
your parameters that went in are correct giving that result. Because there could be 10 other ways
Right.
you can put it together to get that result.
Exactly.
You agree with that?
I agree
Yes.
with that.
Yes,
I
good.
agree.
I think we all agree with that, absolutely. But the problem is that, especially these computational models, are very expensive. So you can't run them 1,000 times to explore that large parameter space and see if those degeneracies that you're talking about are present. So what was
So
traditionally...
degeneracy is when two different models give the same result. So we say those inputs are degenerate to each other.
Correct.
So it's an interesting word in our field
Yes.
to reference that.
Exactly,
Okay, go on.
yes.
It has nothing
So-
to do with their moral.
Thank you for clarifying.
Yeah, I just.
We don't want to get in trouble here.
Yeah. Degenerate computer simulations. Yeah, okay. What are you calculating? Right. Okay.
So what most people did was to take the nearby universe where we had lots of observations. We think we know how star formation works. We think we know how, when supernovae explode, how do they affect the next generation of stars. We even know a little bit about how black holes affect galaxies.
We have multiple telescopes.
We have
working
many
on
telescopes. We have
nearby.
lots of observations. Exactly.
It's resolved.
So we turned all the knobs in our models to match the nearby universe. And then, at least what many groups did, what my group did, was to say, well, what if we now take those models where all our knobs are fixed to match the nearby universe, and we predict what James Webb should see? And you were accusing us of never publishing papers that disagree with the observations. Well, we did. We published a paper before Webb launched, predicting what it should see, and we disagreed with the observations, right? So we learned something. We learned that the physics we put into our models...
learned that you were wrong.
We learned that we were wrong, which is fantastic, right? That's science.
Okay, yeah, that's definitely science. So, but you're wrong in an interesting way.
In an interesting way.
Yes. So, not to deliver your punchline, but that tells you that either James Webb is flawed in the data it's reporting, or you cannot backstrapolate to the early universe from parameters of the galaxies that are nearby.
Or maybe you have to do it in a smarter way, right? So one of the things that we've realized recently is that the environments that are common in the nearby universe are not typical of the early universe at all. So it's maybe as though you tried to extrapolate from New York City, properties of the Sahara Desert or something, right? Of course you would get it wrong. So you need to look for environments in the nearby universe that are similar to the early universe. And what was different in the early universe? It was much denser, right? So there might be various differences. It was much denser, there were fewer heavy elements.
Well, just to be clear, it was denser because all the same matter was in a smaller volume.
Exactly. The universe has been expanding all this time. That means it was much denser in the past.
And in fact, redshift 11, which I think is around to now, how much has the universe expanded over a redshift of 11 to today?
By a factor of...
Is it just linear? Is it just linear? I think it's just linear.
Yeah, it's just linear.
So it's 10 times bigger, 11 times bigger,
yeah,
12
times.
Oh, plus 1.
Plus 1.
Plus 1.
Yes.
Plus 1 in the equation.
Yeah.
I just remembered that. So it's 10 times denser back then.
Exactly.
Gotcha.
No,
Okay.
it's
Okay.
10 to 3. 10 to the 3 times.
So
Its
it's
density is over
cubed.
volume.
Oh, excuse
It's
me.
the cubed. So
Cube
it's
of-
thousands of times denser.
Yeah.
Got it.
Right.
10 times 10 times 10.
So actually, if you look at how stars form in those kinds of environments, which are rare today,
But you can find them.
you can find them. Star formation is much more efficient. And if we put that into our models, then we actually reproduce the Webb observations, and we predict that there should be many more bright galaxies even further away, even at higher redshifts.
Ooh. So in hindsight, you could have actually predicted the right answer.
That's the frustrating thing.
Yeah, because I was once dining with Stephen Hawking, and I asked him a question. It takes him a while to process your question and then type it out with his blinking eyes. Okay, so I asked him a question about why didn't Einstein predict black holes, which come right out of his general theory of relativity. And so it took about 10 minutes, and then the answer came back, you can't think of everything. I was like, wow, okay, that's good. You can't, he would be thinking of you, can't think of everything in that moment. So, were you going to say something here? Because I'm going to match you with another question. Yeah.
Yeah, there's oh, wait. You're talking to...
No, you, yeah.
Okay, yeah, so I think another difference in the early universe is that there were no stars in the galaxy. There was no galaxy. So you have all this gas coming into a dark matter halo, and it has nothing to compete with. So you get this huge burst of star formation. And otherwise, if you compare it to today, there's already all this star formation that's going on, supernova going on, but this was a pristine environment.
But just a quick question. Priya, the dark matter, he just said it's in a dark matter halo.
Yeah.
So is dark matter running the show back then?
Yep, it's in the driving seat. Basically, this dark matter, which is about 20-25% of the overall inventory of the universe, provides the entire scaffolding in which you form galaxies, all of this gas gets collected, black holes form. These are sort of the cradles where everything really happens.
But Priya, you don't know what dark matter is.
Precisely. When I say don't know what it is, we know how it manifests. That's the crazy thing about both dark matter and dark energy. We don't know what they are fundamentally. Like for dark matter, we don't know what particle is a dark matter particle. We've been looking for it for decades.
If it is a particle at all.
At all. And similarly for dark energy, we don't know its nature, but we know exactly how they manifest in the universe.
So you get to put it in your models.
Absolutely, yeah.
Okay. Wendy, when you're calculating the age of the universe and the galaxies and near and far, does dark matter matter?
Oh, yeah. I mean,
in what way does it show up in your calculation? And dark energy, even?
Yeah, if you're going to study the expansion of the universe, it's changed over time, and it's reacting to the presence of dark matter and dark energy, and it folds into the age. If you're going to determine the age, you need to know.
So maybe your wrong age, maybe, according to Michael, maybe your age is different because you're not properly modeling the dark matter and dark energy.
So,
is that possible?
Okay, so step back. What we're measuring is when we're measuring the Hubble constant, we're measuring the Hubble constant at the current time, the current epoch. So we don't need to know. We don't need to know that model. But when we're comparing with the observations from the early universe, the microwave background observations, that's
the whole other method.
The whole other method
from the back door.
It fits these tiny little differences in the temperature of the background radiation, and it fits exquisitely well the standard model that includes dark matter and dark energy. And so the current tension is between the fit of this standard model, which predicts what the expansion rate would be today. It's a predictive model. It will tell us what the expansion rate would be today, given the amount of dark matter and dark energy, and what we see locally. So that's where it comes in that possibly, if both are right, we're learning something about the standard model. Something fundamental is missing in our current picture. That's why it could be very interesting.
Michael, this sounds pretty tight, what she's describing here.
That's right. So I think that actually makes this really appealing because it means that there's not much space to look. We really know what we need to do.
Something's really wrong.
So something is really wrong, and if it's going to be something that's cosmological, if we need to change something in the cosmological model, we know exactly what it kind of has to look like. It has to be some kind of energy that is like dark energy today, but happens just before the microwave background.
Wait, you're inventing some other thing we don't know anything about?
Well,
we tried everything. We tried everything, and nothing worked.
Once you've got dark matter and dark energy, you might as well get a third one. Right? No, it's but I think that's
wait, you're pulling this out of where?
Well, but I think that's the amazing thing, right? Like Priya was saying, we haven't detected dark matter directly, we haven't detected dark energy, but we know so much about observations of the universe from the earliest times to today that we can say this is how they have to behave. So what we're saying is the only way out, if it's not something with our models of galaxies, is
yet another thing that we don't know anything about.
That's right. And we should be able to know if it's there or not within the next year or two.
Priya,
that's the
Priya,
I think
what is he saying?
No, I think he's saying the absolutely right thing. So basically, dark matter and dark energy set the clock of the universe. So if there's something different about them, the clock is different. It ticks faster in the early universe, maybe, slower later, or vice versa. So if dark energy could be changing with time, that allows for a clock that is different, that moves and runs differently. And therefore, all the action that happens in the universe will happen at a different pace.
You're saying something. He's saying there's a whole other mysterious. You're adjusting the behavior of dark matter, dark energy over time, possibly to explain the discrepancy.
That's the first simplest thing we can do.
But Michael is just pulling something else out of the ether.
That's kind of you to put it that
Yeah, right, that is either. But the beauty
Wendy.
of all this is that it's testable, right?
Yes.
If this is correct, it will show up. And it may show up in the next generation of microwave background experiments. There's a prediction. If there is this early dark energy, you're going to see a fairly whopping signal.
Let me jump back a little bit of history here. Priya, you also studied history of science and philosophy. In the history of science, there have been many examples of a prediction of something that kind of had to be there because first there was a good theoretical model for it, but also, what am I thinking? I'm thinking of like neutrinos, for example.
Yeah.
They were predicted because something else was happening in the experiment.
It's a missing energy.
There was a missing
energy.
There was a missing thing, and they said there's some mysterious particle that is nearly impossible to detect that we invented to explain what happened, and sure enough, it existed.
Yeah. I think we have these wonderful laws.
Okay, so that means
right?
I got to agree with.
Yeah,
Michael?
I think all possibilities are open, right? So the fact that we have conservation laws, conservation of energy, allowed us to infer the presence
Of the
this
neutrino.
dark entity,
Yes.
right? And I think similarly, it's quite possible that it's going to be the data that is going to show us the way, right? So future data, better data, more accurate data will really show us the way in terms of what are these specific models. There's tons of models.
So the James Webb Space Telescope is not good enough for you. You need another
I want
telescope.
more. I
It's
want more.
pretty good. It's
Big
pretty
fan.
good.
It's pretty good, but we want more.
It's a tough crowd, I tell you here. So John, you say you use super duper computers. Sorry, just supercomputers.
I wish
Yeah.
I could call it super duper computers.
I mean, supercomputer has been a term for the last 40 years, ever since computers got good.
Yeah.
And at any given moment, there's the supercomputer, of the year. Is there something you can imagine you would do with a computer that's 10 or 100 times or 1,000 times more powerful than what you have right now? And of course, I'm thinking of quantum computing. It's still a little bit of a pipe dream, but what simulation is out of reach to you now that you can't wait to get a super duper computer applied to it?
So I think our problem in cosmology and galaxy formation is just the disparate length scales that are involved with galaxy formation. Right? We have everything from the quantum scale, atomic scale, all the way up to cosmology, in which we have to model.
And it all matters at some level in what you're creating.
That's right. So you have, even if you want to study how stars form in a cosmological volume, that's still a huge orders of magnitude difference in between that, and that's what takes a lot of time. If I had a computer that was 1,000 million times faster, we could get more statistics, but I think it really takes person power to actually utilize those supercomputers. We need like algorithms and people to actually write efficient code to use like millions of computer cores. Like
Just get AI to do it.
And yes, yeah, I'm very excited with AI, but not to write, maybe to help write the code a little bit, but to actually use, say, I know this is probably 1 hour retire, but if AI and quantum computing come together, maybe that will cause us to actually simulate a lot, but
You just don't want it to achieve consciousness, because then we're
yeah.
we're
I don't want Skynet.
So I'm intrigued by that. Just if I'm going to repeat, if I understood what you said, you have to model things on the atomic scale, on quantum scale,
Yep.
and on the largest cosmological scale, and to do that
Simultaneously.
good. So the computer has to know what every atom is doing in every star in every galaxy.
In principle, yes.
Yes. We black
But
box
we
it now.
can't do that, so we have to have an approximation. These are these knobs that we tune.
Yeah.
Okay, so you make approximations. You say, I think this many atoms in this volume will have this sort of macroscopic property.
That's right. So what I think is like to have AI turn the knobs for us, to actually look for that solution to, so these are called emulators. So it emulates physics. And that's what we're basically doing. So we have some physical model. It has to be grounded in fundamental physics, these AI emulators. But I think like once we grapple with that and make those produce realistic and fundamentally physical results, I think that will be like a huge stepping stone.
Yeah, because I remember at any given time that I programmed a computer, I always wanted it to be faster than what it was delivering for me. Every time I ever did it, I say, all right, I'll make do with this. So I felt very greedy at the time, especially since my iPhone has a million times the power of the computer I used back when I was coming up. So we're just greedy.
And now, we have
Eternally
NSF,
greedy.
Eternally greedy.
I think so. Yeah.
And NSF and NASA, they have these huge computers, but big tech actually outweighs how much computing they actually have in generating and training their AI models.
Okay.
Yeah, so if we can partner with them, maybe.
You see the smile on his face as he talks about this? They're like beams of light.
I'm an AI optimist.
Yeah, it is true. In our field, we love us some AI because it makes our jobs easier. It's the rest of the country that's just freaking out.
Right.
When journalists found out that AI could write their articles, out came the headlines, AI is bad.
Or make videos now.
Yeah. Just wondering. So Michael, let's go back to your version of Priya's. We need to modify dark matter, dark energy. You're going to invent this new other thing we don't know anything about to account for this, and you feel sure that would reconcile these two ages.
Well,
Will it bring your number to Wendy's or Wendy's number to yours?
So that would bring the microwave background number closer to Wendy's number. So Wendy would have been right. But I think,
I'm going with Wendy on this, just so I'm saying.
Yeah, there you go.
She's got more data than you do.
And I think one reason that we might think this is something interesting to do based on the James Webb observations is that that same model can predict earlier structure formation. It can help replicate those observations that we're seeing in the early universe. And so that's one reason people find that to be an attractive model. It was predicted to match up these measurements of the expansion rate. That was why it was proposed. But it turns out one side effect is that things happen faster in the early universe, which is exactly what the observations were. And so that's, like you say, you don't want to just invent things to match one observation, but if you invent one thing and it matches two disparate observations, then you start to think maybe you're onto something. So it definitely doesn't have to be this, but it leads us to think more about it, I believe.
And Priya would agree there's plenty of precedent for just that kind of thing in the history of
Absolutely. And I think, as Michael said, one thing we want to do is there's some other tensions that sort of are there on very small scales within galaxies, the way matter is heaped in the centers of galaxies, where all the action is where the central supermassive black hole is sitting, and so on. There's some tensions with observations. Some have come and gone, and some have stayed. And that model would actually help some of them as well. So you could have one little tweak in the model at very early times that could actually resolve and bring into harmony many more observations.
And that gives you huge confidence that you're doing the right thing. If it brings into harmony multiply disparate
and makes an additional prediction that can be further tested, then I'd be a lot happier.
Because otherwise you're making a post-diction, which is less
powerful.
Powerful.
Yeah.
Right.
As Rachel made a post-diction. Atone for this, Rachel.
But I think it's important to point out, too, some of these models have, they don't solve both tensions at once.
Absolutely.
They go in the opposite direction.
They go in the opposite direction.
And there are also examples from history where effects that you see come and go, right?
Yeah.
Which is why we have to be very careful to understand, is this something that's real, or have we missed something in the observation?
To just clarify that as theorists, right, we always know how to stay in business. So there's a landscape of models, And, there
Like I
will
said,
be
ambulance chasing theorists.
You know,
Always
He
got
looked
something
right
that-
at me. I remember this.
You always
very
have
well.
the paper ready, numbers going.
I was right on your shoulder
Yeah,
when
yeah.
I said that, wasn't I?
but this is, I think, a place where JWST is going to help us.
Yes.
I think we're getting to the point where we're going to learn something very interesting about whether this is real or not. And it's the higher resolution of James Webb and the higher sensitivity, particularly in the infrared, and the ability to make these measurements in more than one way.
Right. I think
is going
multiple
shed light on
independent lines of evidence really
Right.
is going to
Yeah.
help resolve these tensions.
So
Let me
this
begin
is something-
to land this plane that we're flying right now. Wendy, you're deeply involved in a new telescope, a Magellan telescope. It's like one of the most powerful telescopes the world will have seen. Could you just give me just a brief overview of that? I've read a little bit about it, but I don't know why do you need another telescope?
Yeah, we've established.
Hubble wasn't enough for you,
We-
and you need another telescope.
We've established that astronomers are greedy. We want more computing power and we need more light. And so when we're looking at faint objects or we're trying to see detail in objects where we need high resolution, then we need a bigger telescope to do that. So there are 3 big telescopes that are being planned in the world right now, and Giant Magellan is one of those.
That's the one you're involved in.
Yes, so I led that project. I was a founding leader from 2003 to 2015. And it will be built in the Andes Mountains in Chile. And it's
14,000 feet?
No, about 8,500 feet. It's
Oh.
not one of the high altitude
Okay.
sites because it's optimized for optical and near infrared. And it is made, there are 7 mirrors in this telescope. Each one is 8.4 meters in diameter. So there's 6 in a circle, 1 in the center, and the overall resolution is, as it were, for a 25-meter telescope. So this is an international collaboration.
Wait, so it's cheating a little bit, because when we think of the resolution of a telescope, the bigger the telescope, the higher the resolution. But if it's one mirror, that's very hard to make. So you say, I'm just going to make a bunch of smaller mirrors.
Little,
and
27 feet in diameter. Little, yeah.
And each of these mirrors is bigger than James Webb's mirror.
Yes.
Each of them.
Yep.
Every
it's
single
bigger
one,
than
yeah.
the
The
entirety.
entire James
Yes.
Webb mirror.
So why do we need a bigger telescope? It will have 4 times the resolution of James
Right,
Webb.
so you're by the pieces that you're assembling, you bring them together in software or cleverly, and it simulates what would be a single mirror of that diameter, 25 meters.
Correct.
That's like the size of
It's,
this.
this auditorium, yeah, it's big.
Yeah.
This is
Big telescope.
huge.
Yes.
What are you going to look at with it?
Well, we're going to learn more about the early universe. We've got better resolution and high sensitivity. The telescope will collect a lot of photons. It will tell us again about the expansion rate locally. We'll be able to go out farther with this higher resolution and find these variable stars and so on.
So then what do you need James Webb for?
James Webb, so there are different things that you can test with different kinds of telescopes. Its infrared sensitivity gets beyond the dust. So dust makes things look fainter
So
and
the
farther away.
Webb.
Webb.
And yours?
This is optical.
Oh, optical. So it's just it's red,
It's
orange,
like
yellow,
Hubble.
green, blue, violet.
Right.
Got it.
Right.
Got it. It's just a really badass regular telescope.
Correct.
Yeah.
Okay.
They should call it
That's
that.
what you mean.
Yeah, that'd be a better name. Yeah.
And you also have to deal with the atmosphere, right? So you
But-
have to correct for the blurring of the atmosphere.
That's right.
But we
Yeah.
think that we can do
But
that.
we know how to do
Yeah.
that now.
And it's named Magellan because he hung out in the southern hemisphere. It's just a southern hemisphere telescope.
It is a southern hemisphere telescope. That's right.
Okay.
That's right. So, and exoplanets, we're not talking about that tonight, but you'll have high enough resolution and sensitivity that you can actually look at the atmospheres of planets and look for biosignatures, oxygen.
That's a whole other
methane.
thing we're going to do.
Whole other.
Biomarkers.
So
and
lots more to do. We're not solving all the problems tonight. You
Exo-
probably couldn't tell that. There's stuff left to
exoplanets.
do.
So Priya, what's your philosophical view on? Are we ready? Is there some paradigm shift? We've heard that term before in our understanding of the early universe. What of these headlines? Oh, astronomers have to go back to the drawing board and might have to rethink the Big Bang. Is this not one of those cases, and that's just clickbait?
Yeah, I think we don't have to rethink the Big Bang, but there are details about our models that we don't really understand. And as Rachel pointed out, all of us have talked about.
But that doesn't make good clickbait on the internet.
Right. But I
There's
mean,
some details of their models they don't understand.
No, but we are in the midst of a revolution in terms of data. So I think it's a new kind of revolution that we have not seen before, where we have no scarcity of data. So there's a lot of data, actually a deluge, which really restricts the job of theorists. We can no longer sit on a fence and say, well, maybe it can be this, maybe it can be that.
The data is constraining you.
Very tightly, soon it's going to start really tightly constraining the models, and hence our theoretical understanding.
That's a good thing. That's a good problem.
Absolutely, absolutely, good problem to have.
It'll give John less latitude, and he'll have less fun at the computer, but it'll bring him in line.
Yes. No, but then remember, we always also have this additional challenge of the storyline. So we need a self-consistent unfolding of all these elements over time. Dark matter.
That can't be overstated here, because you can fit something
Exactly.
then, you can fit something now, and if the arc does not work, go home.
Yep, absolutely. It's not good enough.
Okay. Rachel, why is it that I also saw in headlines the universe might be twice as old as people previously thought? Who's saying that? What is that? Do you remember those headlines? Who? Michael?
The Big Bang was
actually
wrong
not.
too, remember?
Yeah, so there's somebody who wrote a paper on this recently, and what he's done is he's changed...
When you say paper, you mean a research paper that was peer-reviewed?
Two peer-reviewed research
peer-reviewed
papers, and they argue that we really do need a fundamental revolution, not the Big Bang itself, but in our understanding of the matter and the energy content. So he does away with dark energy, he does away with dark matter, but he says that light behaves differently than what we think. And the fundamental constants of nature that we think are constants are now not constants.
Yeah.
So now they're the fundamental
vary.
variables of nature or whatever.
Okay,
they
so he's
change
doing
as
what
well.
you're doing, John. He's saying, let's turn the fundamental constants into knobs. And let's turn the
fear into my heart.
let's turn those into knobs and adjust those and see if you can fit things.
That's right, and so that he is claiming, based on these early galaxies from the James Webb Space Telescope, that that model fits the data better. But I think that there's a lot of other data out there. This model would not fit that as well. And one of the things that we see around us, so that this model would predict the universe is 26.7 billion years old.
So that's these headlines that must have been going
That's
around.
right. But we can measure the ages of the oldest objects in the universe, and we've been doing
They're
this. Is how
definitely not 27
They're
billion.
not 27 billion years old. They're very consistent with this 13,
Was this a physicist
14
who
billion
knew no
years.
astronomy who published this?
Why
did it get published?
Well, I think it's a good thing, to be honest. The clickbait headlines may be less good, but I think that our models are best when they're tested the most severely, right? And so they can take it, right? If the model's right, somebody can throw this at it, and we'll find a hole in that in their model, and the current model will be right. If the current model is wrong, then we'll find the holes there.
Wouldn't the peer reviewer have said, if the universe is 27 billion years old, we would have found something older than 13.8, 13.7 billion,
Give or take.
and there's nothing in the
100
universe that old.
So
So the universe spent half its life making nothing?
Well, I think that certainly some peer reviewers would have said that, and you could say that any peer reviewer could have caught that. But the domain expertise, you need to know lots of different pieces here sometimes, and it's just not possible for some people to know everything.
But also,
Can't know everything.
But also, we are open to speculation as scientists, right? I mean, our understanding is provisional, given what we know at the moment. So we are open to speculation. So if it resolves a problem,
I'm all with you on that, but aren't there people, cottage industries, that test the stability of the constants over time?
Yes.
There's a whole
Yeah.
industry
Very
of
strong
people who do
constraint.
this.
As a peer reviewer, then you would ask, why do you believe
yeah.
this is not the case? And we would ask you to ask the authors to put it in their discussion, saying, prove this is the case.
Yeah, the
why is
caveats.
The caveats.
Yeah, okay. All right. Well, I follow what people do with the physical constants, and it's remarkable that, let's go back, not to be too historical here, but after Newton's laws of gravity were established, and it explained our moon going around Earth and Earth going around the sun, it also explained Jupiter's moons going around Jupiter. That was no one saw that coming unless he was onto something, quote, universal.
Yep.
Then maybe it only works in our own solar system. Must it work around other stars. So when the first binary star system was discovered, it also fit Newton's laws of gravity. And so we've been systematically testing the applicability of the laws of physics so we're not just hoping that it persists through time and across space. We have good evidence for this.
Well, and not only that, it allowed us to predict the existence of Neptune. I mean, us is not me. It was a long time ago, but
Oh, you weren't there?
Yeah, almost that old. In the 1800s, Neptune or Uranus had a little bit of a wobble in its orbit that people couldn't explain from Newton's laws, unless there was another body there.
Oh, so that's right. So exactly right. Because when Uranus wasn't following Newton's laws either, they found the limit of Newton's laws in the universe, the distance beyond which it no longer applies. That's like your people changing the laws of gravity. Or hypothesize another object whose gravity you have not factored in to computing the orbit of Uranus.
Well, and to go further, you're going to talk about Mercury. The orbit of Mercury didn't fit. And the question was, is there another planet somewhere that's perturbing?
Right, and they thought it was Vulcan.
Right.
They thought,
and it
They invented Vulcan. They pulled that out of there.
Well,
but then
it was a reasonable hypothesis, and it was wrong, right?
And that was a problem with
right, and
that was
one of
new
the things
physics.
that
exactly. You needed a fundamental rethinking
General
of gravity
relativity.
itself, and that's where Einstein's theory of general relativity comes in. Right?
So has this other paper caught on with the...
With the press, yes. With the scientists, I think.
But I never heard about it.
You hadn't heard about
that
it?
I
tells
haven't
you
heard about
something.
it either.
Yeah, I've seen it.
Okay.
I get a lot of emails from people saying, Mike, what's going on?
All right, let's now land this plane. If I just get some final reflections on various topics. You mentioned the Chandra Space Telescope. This is one of the
Flagship missions of NASA.
As was Hubble,
Yeah.
and there's a Spitzer telescope. Each one has a specialty. We just learned days ago that the Chandra telescope will likely have its budget zeroed.
Within 2 years.
Within 2 years, and they will have no access to the X-ray universe.
We will lose our X-ray eyes into the universe, which I think is a disaster. And the telescope is working. I think it should be funded for a little bit longer. And the idea was to phase it out as it starts to
And bring
age.
something else up.
Yeah.
But we're not bringing anything else up.
Well, there are plans. There's been a call, and there have been people who've put in proposals for other X-ray telescopes. And the Europeans are putting up an X-ray telescope called Athena.
Athena?
Athena. And
Well, I wish you well there. I mean, that's a tough time. I mean, the telescope is 25 years old.
Yeah.
But if it's still working and we got nothing else, we'll be out of the game.
Yeah, and more importantly, I think we need something to bridge, to kind of bridge our view into the X-ray universe, because one thing that we haven't yet discovered, right, which is something I want to happen before I die, well, I hope I don't die that fast, is the LISA mission, the gravitational wave detection from the collision of two supermassive black holes. We've detected the collision of two stellar mass black holes, the LIGO, the apparatus on the ground that made this discovery. The supermassive black holes also collide, and that will happen in the 2030s. We definitely need some instrument to be looking at the universe with X-ray eyes continuously till then, because the supermassive black holes, just before they merge and that sort of burst of gravitational waves comes out, there's a lot of action in the X-ray that happens beforehand.
You can predict that.
Yeah.
So these two colliding supermassive black holes would be the consequence of two galaxies colliding, and they each have their own supermassive black hole, and they'll probably find each other, given the dynamics of this.
And in that process, there'll be a lot of crud. All the gas and the stuff would be mixed up, and we should be able to see it in the
Crud,
X-rays.
is that an official word? Okay. John, you were beaming when you were reflecting on AI and quantum computing and supercomputers. You were like a little kid, right, in your enthusiasm for that. How soon do you think that'll be with us?
So AI, we're in the midst of that revolution.
Definitely, but the computing power?
The computing power? I mean, I think the hardware is still ramping up, but it really takes people to develop those algorithms and to make the computer code, the simulation code, to fully use the computers efficiently.
So we need more coders out there.
Yes, yeah.
to come up in the
most
ranks.
Students, they are good coders, but to actually use these supercomputers at that scale, it requires a different level of thinking of how to distribute that work among a million cores, right? I mean, a computer, like imagine if you have 1 million computers, how do you split up the work and make them talk together on the order of like, nanoseconds and to just march forward?
A billionth of a second.
Yes.
Yes.
Billionth of a second.
Why not a picosecond? Why not an attosecond? Why limit yourself? That's like saying, I'm old enough to remember if your computer had megabytes of storage, that people lined up to look at that.
So I think because chips, right, when you look at how quickly the frequency of the chips are, they're in gigahertz. So you take an inverse of that, and that's nanohertz. Or, sorry, nanoseconds. So that's the amount of time it takes for a computer to, say, one operation. So it's not going to take... Today.
Yeah, okay.
But that requires a lot of power, and you have to dissipate the power. So it's not going to become, I don't think, anytime any quicker than that. But we can do many more synchronous operations.
Rachel, at the CCA, what are your next projects there? Are you done with James Webb, or is there more data you're waiting for, or you're going to direct it to do?
Oh, James Webb is absolutely not done. That's the exciting thing. So it turns out that originally, Webb was sort of spec'd to last for 5 years, but the launch went so beautifully that we now are hopeful that Webb may last for 10 years, maybe even longer, maybe even up to 20 years.
I thought it's passively cooled. So what is it you would run out? Oh, is it the stability of its orbit?
Exactly. It's keeping the orbit stable. Otherwise, it will drift away, and we would eventually lose the ability to communicate with it. So we need to keep it in that nice orbit close enough to the Earth that we
I know it's 1 million miles away, but let's just go there and drag it back where it's supposed to be.
So there's so many things that we would love to do with this telescope.
Because unlike Hubble, you can't service Webb.
Yep.
Probably not.
I'm sorry. Unlike
Not right
Hubble, no one's going 1 million miles from Earth.
Humans cannot service Webb. It's possible we might be able to send a robotic mission to service Webb eventually.
To drag it back where it's supposed to be.
So there are some people who are thinking about that.
Okay.
But we want to look at much larger areas of the sky. We've only looked at very small patches of the sky, and some of these things we're seeing could just be flukes. We want to go much deeper. Then we predict that we should see many more objects that are even further
With the
away,
new models that take you there.
as the
Very nice.
models predict.
Okay.
And we want to get many more spectra, which will allow us to tell how many heavy elements there are there hidden black
You
holes?
could say metals. We've been through that.
Yes.
How many metals there are. Yeah.
We speak the lingo. We should be able to see these signatures of the growing black holes. So there's many, many exciting results.
Beautiful with that new understanding. Very cool. Well, keep at it. And you're full-time there now, formerly at Rutgers,
Correct.
New Jersey. So welcome to Manhattan.
Thank you.
Flatiron Institute, because it's in the area of the Flatiron Building, which is right there at 23rd and Broadway.
23rd and Broadway is the Flatiron building, but our building is actually at 21st.
What's the Flatiron District?
Correct.
That's why you get it.
Yes.
Okay, well, welcome to town.
Thank you.
For that. So, Michael,
Yes, sir.
why do you look at me like that? What kind of theory is left for you to do with pencil and paper? If most of the action is in models and simulations and the data?
I think it's a fair question, and there isn't as much, certainly, as there used to be, but I think there's always room for trying to understand the very basics, and when you're adding in sort of extra components of matter or energy, it really is, the laws of physics tell you that the energy content of the universe controls the expansion rate, and so you can do this. Okay, maybe you don't need 1 million processors, you just need one processor, but you can just make a plot of this, and that's basically pencil and paper calculation to see how that affects the age of the universe, how that affects the relationship between the redshift that we see something at and the time that we associate with that into the universe.
So you're not using software, hardware, you're using wetware. The brain
That's right.
is wetware, I think. It's still called that?
I think so, yeah.
All right, sounds good. Now, Wendy, so you're going to have the biggest telescope in the land.
I hope so.
And when does it come online?
Well, that depends on funding. So it's totally funding limited now. The project has been reviewed, all the technical milestones have been reached, the site has been leveled, the hard rock excavated, there are dormitories there for people to work, and the mirrors have been cast, so
You're just waiting for money.
we're waiting for money.
How much money do you need?
A lot.
How much?
Who's got a hat to pass?
Take the collection plate here. Well, how,
So,
Would that be
you know,
interesting? If in science we did that, you know?
What?
You come here,
Your
really cool
hat.
project, and we just send around a hat. So,
well, no, I mean, the community actually has been really generous. The astronomical community has benefited from private philanthropy. That's been true since the time.
since the
of the
beginning?
Yeah.
Oh, yeah.
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 And so a lot of the
Keck
money.
telescope is private money.
That's right.
Yeah.
And the Magellan telescopes were private money, and a lot of the
Because telescopes have very long life expectancies, because we change out, they're just buckets to collect light, and the detector at the business end is what can improve over time. So you can have a telescope that you name in a naming opportunity in 1 decade, and it can still be going strong 6, 7 decades later.
And a lot of the funding for the Giant Magellan has come from private philanthropy.
So how much more do you need? You haven't answered my question.
In the ballpark of several $100 million. It's a lot of money.
No, not if you. We got more billionaires than ever before. There's lunch money for them.
Can I, enlist you? And
So Priya, I want you to take us out as a student of philosophy and the history of science. Where are we today in this field? And do you foresee that in 5 years, 10 years, 20 years, a completely new understanding of all of this will emerge? Or is this going to be tight, and maybe there's just something different we'll understand, and we'll plug this into that broader, bigger view of what's going on?
I mean, I like to think that this is just the start of a major kind of revolution that is going to completely transform our understanding. However, we've never been able to predict the future of science itself. I don't think Copernicus ever imagined in 1543 that we would have the capacity to have the Voyagers leave the solar system. So I'm not going to speculate exactly, but I'm going to enjoy the thrill of the moment. I mean, these revolutions are just remarkable. And to think that we, with this little gelatinous thing that's in our heads, aided by
Talk about your own head.
Yeah, small head, are able to figure out so much. I mean, it's astounding. I mean, I am in awe of the universe and the capacity of collaboration and how science has worked and reason. And I just find it really unbelievable that there can be science denialism, given all of this, right?
I didn't see it going there, but that's where it landed. Wow. 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 Yeah, so it is interesting. We can make these discoveries and people run around, I don't trust science. I saw my YouTube and they told me not to trust scientists.
Right.
I'm not going to get vaccines
No.
because they don't understand, but this goes on. We live in that world.
We live in that crazy
But
world.
I'm going to end with these two questions to you. You talk about our gelatinous brain. Are we smart enough genetically as a species to answer the questions we have posed about the universe? Or deeper still, are we smart enough to even know what questions to ask?
Oh, I like that. That was a really beautiful second question. I think that there
We're
is
all just
no
touching
reason.
the elephant.
Right.
We'll never see the elephant because we have no idea what we're touching.
Right. I think that regardless of whether we as individuals have the capacity, I think this is where AI is going to be interesting. It's going to augment our capacity to understand, comprehend, and take in a lot of information and data and process it in the ways that we tell it to process.
So I like that. So it's AI augmented intelligence rather than artificial intelligence.
Yeah.
Would be a more sensible understanding of this.
Yeah, and I think that is the way of the future if we, but then on the other hand, something could explode, right? This is science, we don't know. Something could fundamentally shift. And maybe there'll be a way to cognitively enhance ourselves genetically. I don't know. I mean, that's possible too. right? You don't sound
No, okay. I just,
lost for words.
I don't want anybody messing around inside my head, that's all.
Oh, I see.
Just one final, Wendy, you had a quick
So I
comment?
love that we're in this philosophical bend, and it's probably a good place to end, but can I inject a practical thing having to do with data,
Please.
And JWST data, and so our group right now, in these questions we're discussing right now, we have a JWST program to try and measure the expansion rate in 3 different ways, all in the same galaxies. And we've done something, we've blinded ourselves, like literally. We've taken the data and we've added random numbers to the different catalogs, encrypted those random numbers so that nobody in our group knows what the final answer will be. And we're doing all of the analysis in this mode of there's just fake numbers that are applied to the data so that we don't know where this is going to end up. It hasn't been applied to this program before, but we are this close to having an answer. And so in 3 different ways, so either, all 3 are going to agree, not agree, 2 might agree, I don't know which ones, but we will be able to do that very soon. And I'm really excited about this because I don't know where this is going to land, and it's going to be fun.
So ways of testing the integrity of your observation or your models.
Yeah.
Yeah, very, very cool. Well, I like that, and I like the future. I like what I see here and what you've all said and the angle with which you have approached the nearby and distant universe. I'm much more comfortable in this universe, hearing that we have some really smart people on top of this situation. Join me in thanking our panel.